Just give me a minute. So in last class, we stopped at uh, this slide, so where we were discussing about the characteristics of reciprocating compressor. And we saw that the power demand by the compressor is a strong function of evaporator temperature. If you maintain the condensing temperature constant, you get a curve of this nature. Okay, so this is the power demand by the compressor, and hence the motor has to meet this demand. Even if your operating condition is over here for a domestic refrigerator, in case you do not have any control over the RPM of the compressor, that is, it is a fixed speed compressor, or if you have only single cylinder, so you cannot cut off the cylinders to reduce the power demand. So if you have no control over the power demand, then you will have to go through all this peak power required and then come to your rated power. So your compressor motor has to be rated to deliver this peak demand. And this will happen every time you come or every time you pull down the temperature from the ambient to your uh, desired temperature. Now, fortunately for ACs, you will see that you will most of the time will be operating over here. Okay, so anyhow, even there also you would have to size your compressor for this evaporator temperature, and it is quite close to your minimum rated temperature. Most of the ACs will come with a minimum rated temperature of 16 degrees. Only the central ACs and all may have a certain different lower range of temperature, but all your domestic air conditioning systems will have a minimum temperature setting of 16 degrees C. So you'll be very, very close to the peak demand. Okay, so and your rate, and even if you don't operate at 16, you will be operating somewhere in the vicinity of 20, 22. So very close to your peak power rating. Whereas for a domestic refrigerator, unnecessarily you will be coupling a very large motor to your compressor. And that is why it is recommended that if you are not moving out of your house for several months, maybe if you are going on a holiday for a few days and so, then no need to turn off your refrigerator. Uh, it is not going to harm your refrigerator as such, even if you operate it continuously for those days. And nowadays we use stabilizers in case of power cut, power spikes. So not an issue. Rather, if you turn it off for several days and turn it on again, then it creates an issue. It demands a lot of power from the motor to pull down the temperature. Okay, so same goes for cold storage units also. So even when the cold storage units are working at partial capacities and all, this is true for all old cold storages which had fixed speed compressors. Okay, so they have multiple cylinders, so they can cut out a cylinder or two to reduce the or to match the load. But then below a certain region, again, you'll have to either turn off the compressor only. So over there also nowadays people are replacing those fixed speed compressors with variable speed because it gives us much better control, and also it reduces all these overloading of the motor. Okay, please remember this is different from the initial startup torque or startup current demanded by an induction motor. So this is purely from the compressor side. We are not discussing about the motor. So your induction motor, just during the startup, a single phase motor will have a starting coil, and that will demand more current, and hence on the grid you will have a lot more demand. So a 1.5 ton AC should demand around 6 to 7 amps of current during steady operation. But if you have those fixed speed compressors, just when it starts, it will demand close to 14 amps. Hence, we connect it to a 15 amps power socket. Okay, whereas the modern inverter ACs, they can modulate their speed and create a soft start. That is one thing. The next thing is uh, the motor itself are different in principle. So the demand from the motor side is also the demand. So now if you look at the torque versus the speed curve for the DC motors which are being used nowadays, brushless DC motors, their curves are different from an AC induction motor. So let us just have a quick discussion on how the operation and the characteristics of an actual compressor will differ from the ideal compressor which we have been discussing in the previous class. So what are the idealities we have discussed is we have assumed that the compression and re-expansion is isentropic. Okay, so it will not be isentropic. There will be some amount of heat transfer which was not accounted. Okay, so this is one non-ideality. Then we never discussed about the frictional losses. Okay, now frictional losses, one is of course the mechanical friction. Okay, but even if you discount the mechanical friction, you also have the frictional pressure drops because of the flow. So in your reciprocating compressor, you have two valves, one valve which open inward into the cylinder. This is the movement of this valve, goes down and back up, whereas another valve is moving on the outside of this. So these are the two valves which are placed on your valve plate. Now your refrigerant, when it enters, it has to enter through this small opening that is created by movement of this valve. So that also acts as a flow restriction. So there also you will have some amount of pressure drop or throttling. Okay, so this will also lead to some loss in your volumetric efficiencies. Now, why I'm saying about the loss in volumetric efficiency is, see, you expected a pressure equal to P evaporator during the suction period. Okay, so this is connected to your evaporator. But in the cylinder, the pressure will be lower than the P evaporator. So while discussing about the amount of mass that is trapped inside the compressor, we have uh, discussed that this is the volume into which the refrigerant gets filled. Okay, but you will not have P equals to P evaporator at which the flow or the suction will happen. You will have to go to a pressure slightly lower than that in order to overcome this pressure drop. Okay, so in order to move this valve, you have to apply some differential pressure, and you will see if you have place a pressure gauge over here and a pressure gauge over here, there is a pressure drop. So basically what it means is the piston has to move slightly uh, towards the bottom dead center in order to create that suction. So this much amount of displacement volume is then lost. So during this period, you may not have any significant suction. Okay. And while we were looking at m dot equals to rho e times the metavolumetric efficiency, okay, and then multiplied it by the displacement volume. If this was the expression, now it is not rho e, it should be the density at this lower pressure. Okay, not at the evaporator pressure. So you will have losses in your the amount of mass flow rate that the compressor can deliver. Okay, so if you had assumed an isobaric suction where P equals to P evaporator, whatever amount of mass flow rate you were able to derive, that would be a theoretical derivation only. The actual one would be lower than that. Okay, same goes on the compression phase also. So you will not be able to discharge the gas right at the P condenser. So this is P condenser. You will have to go for a small amount of overpressure in order to lift this valve. Okay, so that will then what will happen? So that will change the PC over PE. So we expected PC over PE to be exactly equal to the condensing pressure divided by the evaporator pressure, but there is some amount of overpressure, so PC dash, and there is some amount of lower pressure required during the suction. So your overall PC over PE is effective. So your RP prime would be greater than the theoretical RP that we were discussing. And of course, you will have losses due to leakages. So leakage of refrigerant, well, it will not come into your thermodynamic calculations, but you will see that the charge, by charge I mean the amount of refrigerant present inside the system, continuously goes down, and that will also have a detrimental effect on your refrigeration capacity. So that is if it leaks to the ambient. Okay, there is another leakage which we only saw it in the lab class. That is exactly what I was discussing. You can have some refrigerant leaking out from the piston ring. So there is a ring, there is a groove provided where a ring sits. It isolates the refrigerant from the case which has your lubricating oil. But of course, nothing is completely leak proof. So you may have some amount of refrigerant leaking from this side. Okay, so that will also change the mass flow rate delivered by your compressor. So in practice, what we do is when we size a system, we have to discuss with the manufacturer and have to get the entire data sheet from the manufacturer. Okay, so manufacturer will put their compressor to a rigorous test in order to get the actual mass flow rate delivered for various pressure ratios. So from there, we have to derive some expression of this sort for your volumetric efficiency. Act means the actual volumetric efficiency. Okay. And then with this actual volumetric efficiency, you have to do the sizing. Okay, so whatever we have discussed in the previous class is all theoretical, ideal, where we did not account for heat transfer, frictional pressure drops and all. But once you get the data sheet will give you the true experimental data for that particular compressor model. And then you fit your expressions. So this is one suggested expression. You can think of other even more complicated expressions to be fit for the volumetric efficiencies. Okay. And with this, you can now extrapolate or interpolate the data and size your system for that particular compressor model. And you can check if this compressor will give you the desired capacity. Any questions?
Sir, can you please explain again how the compressor pressure increases?
Compressor
And
pressure.
condenser, the output of
Oh,
the
oh,
compressor.
oh. This one, this one.
Yes, sir. PC does.
So, see, uh, here the valves, first of all, you have to understand the difference between the valves of the IC engines and the valves which we use in a refrigerant compressor. The valves are not actively operated, so they are passive. Have you have you actually seen the valves, the valve plate, which I have shown in the lab class?
Yes, sir.
So then you know that if you have this plate, okay, so there is a valve placed on this. There is a valve which is on the bottom side of the plate. So this valve will open inwards. Okay, this is your cylinder. So this flap will go down and up, okay, in order to allow refrigerant to come in. And this flap will move up and down in this manner in order to discharge your compressed gas. Now, in order to move this flap itself, you will require some differential pressure. So this is your discharge side. This connects to your condenser. Okay, this is your suction side. This connects to your evaporator. So in order to move this flap up and down, you need some amount of additional pressure inside the cylinder. Okay, which has to be slightly greater than the P condenser. So PC prime has to be greater than PC, so that the valve moves up and the vapor comes out. Okay, so that amount of additional overpressure the compressor has to provide, which means that you expected in the previous discussion that the valve should open exactly at this moment. The valve will not open exactly at this moment. It will open somewhere here. Let's say you apply more spring force, or if you provide a much more rigid plate, it will require more overpressure. If you provide a very thin plate which can open at extremely small delta P, then it will require less amount of overpressure. That's what I was saying. So valve itself will not open.
Okay, sir. Thanks.
It will open at certain other pressure higher than your expected PC. So this is your PC pipe. And this is where you will start discharging.
Yes, sir.
Okay, and one of the most common failure of any compressor is the failure of this valve. So could be that the suction valve remains open, okay. So or the discharge valve remains open, it doesn't close completely. That is a very common failure. So you will see that your compressor will not deliver any mass flow rate. So what will happen is whatever is going out, if the discharge valve, the valve on the condenser side has failed, so when you're compressing, the gas goes out. When you are again re-expanding, the gas is sucked back in from the condenser. So ultimately, you will not have any mass flow rate in your loop. So same amount of mass is being pushed and re-expanded. So that's why there is a third category of compressor. So one is completely sealed, where in order to do maintenance, you will have to cut open the compressor casing, which houses the motor also. The other one is open type compressor, where all these valve plate, everything is accessible. We have a third category, which is in between your sealed and the open type, which is called as semi-hermetic type, where only the cylinder head, okay, and hence the valve plate access would be given. Okay, so we have identified that this is the most common failure, and you can also intuitively feel once you have seen all the how the valves are. So this is the most common failure. So we can replace the valves. On all other components will be inaccessible. So again, the crankshaft connecting the compressor to the motor will not be accessed in a semi-hermetic type. So you can do only the maintenance of the valves. Anything else? So as I have told you quite a few times, both in the theory class as well as in the lab class, that uh, the Bureau of Energy Efficiency, this is a bureau created by the Ministry of Energy. This bureau is tasked with giving the star ratings for all the home appliances. So be it your geyser, your refrigerator, your washing machines also now have started being rated with these star ratings. Okay, and of course air conditioning was the first system with which they have started. So you will see such star ratings over uh, on your indoor unit if you are using a split AC. If you are using a window AC, it will be again on the inside of the again the indoor cabinet of the window AC. So this star rating actually in technical term doesn't convey much information. Okay. So this star rating is like relative grading. So you do not know what is the absolute performance if you just look at the star. So the absolute performance is actually given in this number. So this energy efficiency, okay, EER, so again very common in industry, but not very common in academia. So it is energy efficiency ratio. It is nothing but COP. Okay, now whenever we are looking at COP, we also need to specify the conditions in which we are operating, because we have looked at the compressor characteristics now. Now, compressor itself will deliver certain amount of mass flow rate based on the evaporating temperature and condensing temperature. Okay, the enthalpy changes across the compressor, the enthalpy change across your evaporator. Everything is a function of your operating condition. Hence, your COP itself is a function of operating condition. Okay, so till 2017, all the models came with this EER rating. Now, this EER testing or COP testing was done at uh, a fixed condition. The fixed condition being the outdoor temperature is 35. That is the air entering your condenser is at 35. Okay, and the the air entering your indoor unit is maintained at 27. Okay, so what we have is we will require two chambers. Okay, you place your indoor unit in one chamber and your outdoor unit in another chamber. In this chamber, you maintain 27 degrees C by means of a heater. And in this chamber, you maintain 35 degrees C by means of an additional chiller. Okay, so this is how the testing is done. So it will be connected with two pipes and electrical wire and all those things. And you operate your AC. So it is our task to maintain 27 here, 35 here. And then you will have various probes to check what are the conditions of refrigerant at various points in your AC. Now, based on that, you evaluate the enthalpy difference across your indoor segment and what is the enthalpy or what is the power consumed by your compressor, and you have to arrive at two important things. What is the cooling capacity? Okay, so even if the salesman says it is 1.5 R ton, okay, but you still have to look at this number. So 1.5 R ton is approximately 5.2 kilowatt. Okay, whereas this AC, even though it is rated as 1.5 R ton, is delivering 4960 watts of cooling capacity when these are the conditions. Okay, and what is the power consumption again for these conditions? So this gives you an idea, and if you divide them, you will get this number. Okay. Now, then B has standards that if your COP is within a particular range, let's say 3.2 to 3.5, I will give only 2-star rating. Okay, because As a layman, I don't understand COP, but as a mechanical engineer, star ratings do not make any sense to me because it is a relative rating. I want to know the absolute performance of the system. Then if your AC has 3.51 to 3.8, it will be given 3 stars. So there are certain standards like that. Based on that, that star rating is given. But then quickly the ministry realized that, okay, this is very good from academic point of view because we are doing the testing at a very particular specific condition. But how does it affect, or how does it matter for a layman? Because you and I would be operating it across a variety of outdoor conditions. Okay, indoor condition getting fixed is fine, but outdoor condition would be continuously varying. So then we shifted to something called as the Indian seasonal EER. Okay, so instead of having a fixed outdoor condition, we specified that based on the Indian seasonal condition, the outdoor conditions will have to be varied across a particular range, and the AC will have to operate for several hours at those particular temperature ranges. Okay, so total number of hours of operation of this AC will be 1600 before it gets the star rating. Now, how this 1600 would be divided into various outdoor condition? Okay, so slide is not there. Okay, somehow it didn't turn up. So how that 1600 is divided into several hours of operation is given by this table. So at 24, 25, 26, 27, so like this, your AC will have to operate. And how many hours? 146 hours at this condition, 163 in this, 177 like this. Okay, so again, this is a number which has been arrived at after several deliberations between the company representatives and ministry representatives. And this is now the standard mode of testing. Okay. So you can see this came as a Gazette notification on 8th of August 2017. And this is what we are following now. Now, this is how the star ratings have been continuously upgraded over the past decade now. Okay, so whatever AC was rated as 2 star in 2012, 2013 became 1 star in 14, 15, and it was then removed in 2016 to 2018. So it was phased out. Okay, then there was a major change which happened in 2018 to 2020 period. What happened was many manufacturers started coming up with the inverter models. So variable speed compressors, and they were significantly more efficient than the fixed speed compressors, fixed speed air conditioning systems. Okay, and then our government then thought that this is the right time to discard of the inefficient ACs. Of course, they will not come and remove your AC if you're using a very old model. But if you go and buy a new AC now, you will not find those inefficient models in the market. Okay, so star rating 3 was effectively downgraded in the sense that it became star rating 1. So when a layman now goes into the shop, he will see that 1 star, he or she will see 1 star and he not buy that. But if you look at the absolute performance, it is still the same. So it's like a student getting 50% mark. Earlier was given a B grade and now he'll be given a D grade. Okay, so and then these two star rating 4 and 5, which was still coming under the category 5 earlier, now they were able to differentiate those highly efficient air conditioning systems from the other ones. So let's say you have a AC which gives you 5 as the COP, and earlier the rating for star rating 5 was 4 COP and above. So 4, 4.5, 4.7, 5, everything was clubbed into 5-star. Okay. So now you have a clear idea that which AC is more efficient and which is not. And then again, there has been a steady uh, upgradation of the star rating. So again, from 2021 to 2023, the star 1 will be phased out and star 2 became now the new star 1. Okay, and you can see the EER ratings for the star labels. So now you get 1-star rating for a 3.3 to 3.49 COP air conditioning. Okay, whereas if you were to look in 2016, 2017, you would be sitting on a 4-star rating for the same performance. Okay, and star rating 5 was 3.5 and beyond. So all these all these air conditioning systems were categorized as 5-star. So there was no motivation for the companies to come up with more and more efficient systems. Okay, and the progress that has happened is not only in terms of the compressor. So compressor changes have happened. So we have started shifting from reciprocating to rotary type. That is the rolling piston type compressor. That is the mechanical change. The electrical change that has happened is shifting from single phase A induction motor to BLDC motors. That is from the electrical point of view, and also from the heat transfer point of view, you will see that nowadays the AC indoor and the outdoor unit is significantly bigger than what used to be maybe 6, 7 years ago. So they are not as compact as the ones which you will be having from the older models. So they have also started to invest on the heat exchange area also. Any questions? Okay, so this brings us to the next important device, that is the expansion device. We will look at uh, 3 types of expansion devices in this theory class. So there are various types of expansion device. One is the capillary tube type. I think we have already discussed this in the lab class. Okay, so this is just a passive device. By passive device, I mean that the area through which flow occurs in the expansion device, it does not change. Okay, or it is sometimes called as the fixed opening type. Whereas if you look at other types of expansion valve, that is a hand operated valve. Hand operated valve, an example in your day-to-day life would be your tap. You rotate uh, the knob on the top of your tap, and you increase or decrease the area through which the flow occurs. So that is a variable opening type. Okay, we will discuss about the thermostatic expansion valve because I have shown it in the lab class, but I didn't discuss it in detail. Then there is something called the electronic expansion valve. Again, instead of mechanical actuation, here it is all electronically done, but you have a tap. So I'm using the word tap because we are familiar with that. So it is a valve which is operated through an electronic circuit. Okay, then we also have a float type expansion valve. Float type valve is again used in your day-to-day life. Where do you use a float type valve? You use it daily, a float type valve. How does water fill up in your flush tank and automatically stop once a certain level is achieved? Have you even cared to look into your flush tank? So you must go and look. So there is a floating ball, okay, which is connected by a rod to the actual valve, and this is connected to your overhead tank, and water just simply falls from the bottom side and it fills up, and there is just a small plate which opens and closes, this one. Okay, so when it is at this location, so this will be fully open, so it will allow all the water to from the overhead tank to fall. As it comes up, it will partially close, and when it is beyond a certain level, it will fully close this valve. Okay, so this is a float type valve. So something similar is also used in case of refrigerant also. But they have specific applications uh, for which we need to also discuss about different types of evaporators and condensers and where those different types of evaporators and condensers are used. So only after that we'll be able to discuss where the float type expansion valve is preferred. Since we do not have so much time, so we will skip this. And there is nothing much to discuss about the hand operated expansion valve. So it is basically a tap. Okay, so this is a hand operated expansion valve. So you rotate this wheel, you have this threaded section. This will move up. This will allow this needle to open this particular hole, and you will have liquid refrigerant coming from here. It will pass through this tiny hole and come out on the other side. So you will have liquid here and you will have liquid plus vapor. And why it is liquid plus vapor on the outlet is because you will have lot of pressure drop happening as the liquid refrigerant flows through this tiny orifice. Okay, so that will lead to a pressure drop. So if I were to draw the process on a TS diagram, let's say this is your saturated liquid. The condition at the outlet of this valve would be slightly lower pressure. So this is one isobar. This is the other isobar. Okay, if the pressure drop is higher, you will have this condition. Okay. So all you need is a flow restricting device. So whenever you hear the term expansion device, all you need is a flow restricting device. But then what is very critical about the expansion valve is not only should it provide you the desired pressure drop, but it should also provide you the required mass flow rate at that particular condition. Your refrigerant is flowing into the compressor at a particular rate. Okay, so flowing into the compressor at a particular rate, the discharge rate is also the same. But then when it comes to the expansion device, after passing through the condenser, if your expansion device is too small, that means the orifice is too small, or if your expansion device is too big, that is your orifice is too big for that particular operating condition, then you will have mismatch with the compressor. If the compressor mass flow rate is m dot refrigerant, m dot rf, then your expansion device should ideally provide exactly the same mass flow rate at that particular condition. Hence, sizing of the expansion device is also critical along with the sizing of the compressor. So once you have sized your compressor, you have to buy the appropriate expansion device. Now, which expansion device to be used out of these? Normally, you see EVs are used for large systems. They can be used for small systems. You will get such expansion valves, but they're expensive. So only for large systems you can justify the cost. Okay. Then these float type expansion valves are used for very specific type of evaporator. So for the time being, let's not discuss this. So ultimately, you will see that most of the manufacturers will be deciding between these two, capillary tube and thermostatic expansion valve. Okay, of course, we are not looking at hand operated expansion valve. Nobody is going to sit and operate the expansion valve open and close based on the required load. Okay, so this is out of the question. So either you go for a capillary tube, which is a fixed opening type, or you go for a thermostatic expansion valve. So we'll focus our discussion mainly on these two types of valves. We will discuss how the capillary tube is sized. Okay, a capillary tube is nothing but just a tube, a long tube which has very small diameter. So as far as the cost goes, it is the cheapest one. You just go to the market. If you have sized your expansion device, if you have sized what is the diameter and length, you go to the market, buy a tube of that particular length and dia, okay, and just coil it up. Just in order to save space. That's it, you're done. It is as simple as that. Okay. And if you have the old refrigerators, they used to come with this capillary tube expansion device, because there is nothing cheaper than this. Okay, so we'll discuss how we actually can size this and how it behaves vis-a-vis the changing operating conditions. And the most commonly used expansion device right now is the thermostatic expansion valve. So we'll discuss how this is advantageous to use a TXV, okay, or sometimes it is also called TEV. What is the principle, how it is advantageous, and how again this valve behaves when the operating condition changes. Because sizing for one particular condition is not enough. Your system will operate across a range or variety of operating conditions, and for that your expansion device should provide the appropriate mass flow rate, whatever is based on whatever is demanded by the system. And most important thing is the mass flow rate delivered by the compressor should be balanced by the mass flow rate flowing through the expansion device. If there is an inequality, then either your evaporator will start to flood or it will start to get starved. So if you are not providing, let's draw the cycle. This is your cycle: condenser, evaporator, compressor, expansion device. Now, if your compressor is demanding, let's say 1 kg per second, and your expansion device can only provide 0.5 kg per second, then you will have your evaporator pressure going down significantly. Your evaporator will get starved of refrigerant. So condenser will start to get filled up with liquid refrigerant and evaporator will become starved. And the other scenario where your compressor is demanding only 0.5 kg and your expansion valve is giving you 1 kg per second, then you will have your evaporator which is getting flooded and condenser getting starved. So you don't want these scenarios to happen. So whenever you size a compressor, you have to appropriately size your expansion valve also. Which type of valve is dependent on the application, the cost of the system, your target price. Okay, but what should be the size of the valve? the size of the valve has to be dictated by the size of the compressor, and size of the compressor is dictated by the capacity that you require. So in our lab experiments, you would have actually seen the hand operated expansion valve. So we place it normally along with another valve. So if when the system is not under operation, we want to isolate the condenser and the evaporator, then we can just close the hand operated valve. Okay, or let's say your thermostatic expansion valve is unable to provide you the desired pressure drop, then you can place a hand operated valve in series and rotate your hand wheel to that particular condition where you get your desired pressure drop and mass flow rate. So you can use this hand operated valve to fine tune your system operation. So you can get the desired pressure drop or the desired mass flow rate. And then once it is set there, either you remove this handle so that no one can come and again rotate the knob, or you buy some mechanism you have to lock it. So this is the only application of the hand operated valve. So you can use it just to fine tune your uh, fine tune your mass flow rate and the pressure drops based on the operating condition. But you will not see a hand operated expansion valve used in isolation. So in our lab experiments, you would have seen that there are few hand operated needle valves. So we use it to isolate the condenser and the evaporator. Okay, and you can in fact use it to also change the pressure drops across the system, or rather the liquid line. Okay, so you can change the pressure drop and hence the mass flow rate. Okay, so as I told you, capillary tube is just a long tube with a very small diameter, and this is how it will look like. Okay, so this is another figure. So all you have to do is you have to decide what is the diameter, what is the length. So let's say you go to the market, you buy 10 meters of this tube. Okay, and do some calculation. We will see that calculation. And you finally see that, okay, I need only 4 meters of this tube. You cut that tube up to that length, attach it. You are done. Okay, so this is the evaporator. This is coming from your condenser, the liquid line. There is a filter dryer. What you see, this cylinder. Okay, so in order to catch some debris material, if it is there in the line, before it enters this capillary tube, you have to filter out. So there is a filter and dryer, because while charging the system, you are bound to have trace amount of air, and along with air, you will have some moisture inside. So this filter cum dryer will have a filtering mesh and some zeolite or silica gel to absorb the moisture. Okay, after it passes through that, it goes into the capillary tube, and from here, then it goes to the inlet of the evaporator. Now, as far as the diameter of the capillary tube goes, you see the diameters are typically of this value. Now from this value, you can easily realize that for such diameters, you will not have capillary action. Okay, the surface tension forces are not that dominant for such big diameter tubes. So for surface tension to be dominant, you need even smaller diameters. So even though we call it as a capillary tube, there is no capillary action. Okay, the tube diameters could be as big as 3 millimeter. 3 millimeter is quite a big diameter. Okay, and the typical length that we will get is somewhere between 1 to 6 meters. Now, how is a tube acting as an expansion device? Again, you have to go back to your second year fluid mechanics, where you have studied about frictional resistances offered by any pipe surface. Okay, so you have a property called viscosity, and because of the viscous forces, you will have the frictional pressure drops inside a tube. So if you draw the velocity vectors, even if you have uniform velocity at the inlet of the pipe, it becomes, after some time, it becomes parabolic in nature. Okay, and it becomes of this nature because fluids are not ideal. They have a property called viscosity. So the fluid molecule next to your, the fluid packet next to your pipe wall will come to rest. No slip boundary condition. Okay, so these edges, these circumferential edges will have zero velocity. Yeah, and that will lead to an acceleration of the fluid flow near the center line. You have to balance the continuity. Okay, and that happens across a length of the tube that is called the entry region. So you'll not have suddenly the parabolic nature. You will have something of this nature, no? The velocity profiles, and finally it will turn out to be parabolic if it is laminar. So I'm discussing about the laminar flow. Okay, so all these phenomena will happen over here also, along with another phenomena, which is phase change. So you would have calculated what is the pressure drop expected for a particular length of tube, and you got that friction factor for laminar flow is 64 by Re. Okay, where the expression for pressure drop is FL by D into half rho V square. Where velocity V square here is the area average velocity. Okay, so all those things are valid. Only thing is now you have one additional complexity, that is the phase change. So at every cross section now of this capillary tube, you also have to take into account the changes in density. You would have studied this for an incompressible fluid like liquid water. But now here, your densities are a function of pressure and temperature. And since pressure is changing within the tube, your temperature also changes because it is in the two-phase region. So as pressure changes, temperature also changes, and you have massive changes in the density. So it becomes quite tricky to solve this problem analytically. So I will just quickly go through the mathematics of how to analyze this type of flow. And of course, we will not be analytically solving this. We will use a numerical method to solve. And we will make use of that code to size our capillary tube. So before I discuss about the mathematics involved, let's see some simplifications which we are going to make. We'll assume steady flow through the tube. We'll assume that the fluid properties are homogeneous in in the two-phase region. What it means is when the fluid is flowing, let's say it is liquid over here, and after certain length it becomes liquid plus vapor because the pressure will drop and the liquid refrigerant will change its phase into liquid plus vapor. So if I'm looking at this cross section, this particular cross section, I will assume one homogeneous property. Okay, because it will be very difficult to handle inhomogeneous. So you can have liquid near the wall and you can have more vapor near the center line. So I will not be considering that variation. So at any given cross section, if I know the pressure, temperature, and the quality, so pressure and quality if I know, then I know all the fluid properties and I will assume that as average fluid property across the entire cross section. No variation across the radius of the tube. So all the equations would be written in terms of the bulk mean velocity. Okay, again, you will have this parabolic nature of the fluid velocity as you move past the entrance region. So I will not bring in these complexities because then I will have to do 2D or a 3D simulation. So I want to create a 1D set of equation. 1D, the only variable being the x. So in the x direction or along the length of the capillary tube, I want to see how the pressure varies, how the quality of the refrigerant varies, what is the mass flow rate. Okay, so if you just take a small cut section of the capillary tube, okay, so this is that control volume, and you apply your continuity. So here it is y. So y is the direction of the length of the capillary tube. So it is along the length of the capillary tube. So you apply your continuity equation. You apply your momentum balance. So I'm sure such expressions you would have seen in your fluid mechanics. Here you assume that the density is rho, velocity is v. Okay. Here you assume density is rho plus d rho by dy into delta y. Okay, and velocities would be equals to v plus dou v by dou y into delta y, like that. Very similar expressions you will get, and then you apply your momentum balance. So what is the inlet momentum? What is the outlet momentum of the fluid? Okay, and the difference would be balanced by the shear forces acting on this control volume at the wall. Remember that this shear force is a function of viscosity of the fluid. So if you have a fluid which has no viscosity, then you will get shear forces as 0. Okay, so this is momentum at the inlet, momentum at the outlet, and this difference is balanced by the frictional force on this control volume. Okay, and then you simplify this expression. This is what you will get. I will not bore you with all the derivation of this. And the third equation is the energy balance. First is mass balance, momentum balance, and energy balance. Now, energy balance is straightforward. You apply first law across this control volume. So you will have H in plus half V square into m dot at the inlet. It will be equals to m dot H out plus half V square. Okay, so mass flow rate is not changing across the cross section. So m dot cancels out. All you have is this. Now you would be wondering till now we were discussing HI equals to HO. That was the isenthalpic equation we were writing for the expansion device. But when it comes to actual analysis, you will see that the velocity of the fluid maybe is not significant at the inlet, but it becomes more and more significant at the outlet because the densities are dropping. And when densities are dropping, your velocities will be increasing in order to balance the continuity. Okay, so we will see once I show you the output of the code that the velocities at the exit of this capillary tube will be very high. And we cannot neglect the kinetic energy then. So till now, when we were drawing the process line for the expansion device, we were writing HI equals to HE or HO. But the true equation should be enthalpy, specific enthalpy plus the specific kinetic energy. That is half V square. Okay, so I will not bore you with all this derivation because these are not required per se for this course, but it is good to know that how these numbers are derived. So what we are going to do is we will just now solve this set of three equations. We have to solve these simultaneous equations in order to obtain the diameter and length of the capillary tube for a given PC and PE. Okay, so what is specified is, okay, I need a capillary tube for my refrigerator where the refrigerator evaporator temperature would be -30. The condensing temperature, let's say, is at 40 degree. Okay, this will be specified. What is the mass flow rate required at this condition? That also needs to be specified. So m dot needs to be specified. Okay, because that determines the capacity of the system. So this I would give to you, and now you have to come up with the appropriate diameter and the length of the capillary tube that I will go and buy and attach it. Okay. So this is the momentum balance equation. You will see this is the inertial term, this is the pressure gradient term, and this is the viscous term. Okay, this tau W is this expression. Okay, if you want to see from where I have taken this expression, the references are all given. Okay, and this F itself has the 64 by RE, or if it is in turbulent region, you will have to look into the Moody's chart. Okay. So now one important thing to notice, this capillary tube has a constant area, so area is not changing. So what we can say is rho into V is constant from the continuity. Okay, so that's why wherever rho into V is there, I have replaced it with the expression G, where G is equals to rho into V. And then in order to solve this PDE, okay, I will now use a finite difference method. So where I will, instead of writing this differential equation, I will convert this into a difference equation so that it becomes an algebraic equation, because ES will be able to solve the algebraic equation. Okay, so this is the final form of the momentum equation. So just let us see what it tells is del V over del Y. What it means is how the velocity is changing with the length or across the length of the capillary tube. So in order to solve for this, what I will have to do is I will have to divide my entire capillary tube into small segments. That is the del y. And this del v over del y is how much v, let's say at the inlet of the first node, the velocity is v1 and at the exit is v2. So this gives me v2 minus v1 divided by the length of this node. Okay, that is equals to minus the pressure gradient and this expression. This expression is nothing but the viscous term written in a different way. Now what is this FV bracket? So this is just the average F into V. What it says is there would be a different friction factor at the beginning of the node and there would be a different friction factor at the end of this node because the velocities are changing, the properties are changing across the length. Hence the Reynolds number will also change. Okay, so that's why this F into V, G is constant, rho into V has to be constant. So that I have taken out of this bracket. So this F into V, I am taking as the average of the inlet and the outlet. Inlet and the outlet of this small node. Okay, so this has to be repeated across all the nodes. So here I and I minus 1, these are all the index of that particular node. And then I rearrange this expression and get delta y in terms of the other parameters. Why I am writing this in this form is because my task is to find out the length. Length is not given to me. What is given to me is the PC and PE. So what I will do is I will divide. So while explaining you, I told you I will divide my capillary tube into small length segments. So instead of that, I do not know what is the total length. So how will I decide what is the length segment? What I will do is I will divide my PC and PE. This I know because this is given to me as a design condition. I will divide this entire range into smaller values. So I will segment my PC minus PE. So if your PC is given as 10 bar and P is given as 2 bar, okay, let's say I divide it into 100 segments. So each segment will correspond to a particular delta P. So your total pressure drop desired is 8 bar divided by 100 segments. So each delta P is 0.08 bar. So I know delta P. Okay, and I will try to find out what is the length required for me to attain this delta P. So this is a reverse problem. So pressure drop is given, I have to find out the length. Whereas in your fluid mechanics course, you would have actually solved for length being given and you were determining what is the pressure drop. And the information about m dot is in this expression G. So m dot is also given. Now I will not be able to fix this G unless and until I also fix A. So what I will do is I'll assume some diameter. So assume some diameter. So assume some diameter. From there A gets fixed and M is already given to me because M, PC, P, these are the three information which is given. So M divided by A will give me rho into V, that is the G which is fixed. So this is also known now. Now all I need to determine is first velocity difference I do not know right now. Okay, and I do not know the length required for me to attain this delta P. So these are the two unknowns. So how do I get the velocity? Can anyone tell me? So at the inlet node, let's say I know the velocity. I have to get the velocity at the next node. How do I get that?
Sir, mass flow rate is constant.
Yes, exactly. Very simple. So ultimately this delta V, you should see it as the density being unknown. Because if you are able to find out the density at the next node, you can get the velocity also. Because G is equals to rho into V. G is constant. So at any given node, I need to know what is the density. And in order to get the density, I need to know what is the pressure. That I know because I have already divided my 10 minus to 8 bar into 100 nodes. So I know what is the pressure at each node. That is fine. But I need another information, that is the quality. I need two properties to fix the other properties. So I need to know the quality. So ultimately, this equation now turns out to be an equation to determine the quality and the length. Because once the quality is fixed, density gets fixed. Once the density is fixed, the velocity gets fixed. Okay, and once I know the velocity at the next node, then I can apply this difference equation and get the delta y. So the entire problem now just boils down to obtaining the quality at every node. Now, how to determine that? You have another expression, that is the energy equation. Okay, so make use of that. So we have to make use of that. So if I use the energy equation, this is my energy equation. Okay, and this is my mass being constant. So if I use these two equations, I will be able to get the quality. No? Okay, so if you are not able to visualize this, let's take a node. Let's say the pressure over here is 10 bar and pressure over here is 9.92 bar. Okay, I know the G. Okay, and I know all the properties at this particular location. I need to now get the properties at this particular location. So I apply the energy balance equation. So energy balance equation will give me H out, V out square by 2, H in and V in square by 2. So all these things are known here at the end. How to obtain H out? So your H out is a function of pressure at out, which is known 9.92 bar, and quality at the out. Okay. And as it is, if you apply your mass balance equation, so you assume some quality, you get the density at this node. I'm trying to help you out how the iteration will happen. So assume some quality, get the density, you will get the velocity, and then feed it back into your energy equation. You have already assumed the quality. Okay, you know the enthalpy for this assumed quality. Definitely, this is not going to balance it out. Okay, either you will be above your inlet energy or you will be below your inlet energy. So based on that, you make the next guess. So there are various ways of solving such problems. Okay, there is something called the bisection method. There is something called the Gauss-Seidel method. So you will have to iterate in terms of the quality. Okay, so easiest way what I normally do is I'll assume some quality and check this error. So error is H out plus half VO square minus H in plus half V in square. So this is my error function. I check if the error is positive or negative, and again I assume some other quality. So let's say with one assumption I get the error as positive, with some other assumption I get the error as negative. Then I bisect these two qualities and check again if the error is positive or negative. So this is the bisection method. I don't know if you have studied it in your first year or second year mathematics. So once you bisect, again check for this error. And then you take those two qualities for which you have opposite signs of error, and then again bisect. So let's say for quality 0.9, I get an error which is greater than 0, and for quality, let's say 0.7, I get an error negative. So I bisect it and check at 0.8. If the error is still positive, then I will bisect this 0.8 with 0.7 and then check at 0.75. If the error is still positive, then I will bisect this 0.75 with 0.7 again. Again check. So you can understand now I'm moving towards that actual quality. So this is the iteration which I'll have to do. So then that iteration is required. Now fortunately, EES will do that iteration for you. So if you were to write a Python code, this is how you will have to write. Unless Python also has some, I am not aware if there are certain modules where certain library functions which we can call and solve such simultaneous equations. Okay, so the iteration needs to be done for quality. So once you get the quality, then all the properties are known and hence everything is known for that next node. And now this becomes your inlet for the next node, and you will have to determine the outlet again. So this has to progress till you reach. So you have to start at one end, let's say condensing end, and you reach this. Okay, and for each node, once you get all the properties, you plug in all the values into this equation which is boxed in red and get the delta y. Because ultimately your target was obtaining delta y. So any questions? So I have just tried to explain you the logic behind the sizing. I have not gone through the rigorous mathematics because I have assumed that you have gone through the fluid mechanics subject, heat transfer. You would have done such problems where you divide your entire volume into small control volume and apply energy balance, momentum balance, continuity, and solve the equation. So any issue with the concept? So what looked like a trivial device, yeah, but the calculation is non-trivial. Calculation is quite involving. So let's say you are tasked with this problem. You have to design a capillary tube. So design means sizing a capillary tube for particular refrigerant having mass flow rate of this much for these operating conditions. So as I told you, first step is to assume some diameter, d equals to 2. You assume it within that range, 0.5 to 3 mm. You assume, make an assumption. Okay, and divide your entire, in this case, temperatures are given. So you can either divide it into the temperatures or pressure. That part doesn't matter. So here I have divided the temperature. So anyway, it corresponds to certain evaporator pressures. So each node will have a temperature difference of 1.32, and then sorry, correspondingly you will have the pressure difference. So I don't know if this is visible, the pressure values and temperature values, not visible, no? Okay, now is this visible? The pressure values and the temperature values at each node.
Yes.
Okay. So, so what I have done is I have linearly divided my temperature. So temperature difference across each node is 1.32. So you will have some nonlinear difference in, so it's not constant. So it will be following some other function. So you can either divide your pressures or you can divide your temperatures. The main point is you will have to finally plug in the temperature pressure difference in that equation. Okay, and then for each node, every property is calculated. You see specific enthalpy, quality, okay, and then this is the velocity. You see as the temperature decreases, which means there is a reduction in pressure, which means there is a reduction in density. You can see the densities are reducing. Hence, the velocities are increasing in order to balance the continuity. Okay, and what we assumed as an isenthalpic process is no more an isenthalpic process. There is a small amount of change in enthalpy also, because enthalpy plus kinetic energy is constant now. Okay, so across the capillary tube, the specific enthalpy is not constant. It is the summation of specific enthalpy and specific kinetic energy, which is constant. And you see the gradual change in the quality. The quality keeps on increasing because you will have more and more vapor. And for each temperature difference, I have now been able to attain what is the delta Y. I've written it as DL. So what is the delta Y? So finally, if I have to size the capillary tube, what I will do is I will sum up all these delta Ys. That is the total length which is required. But now there is a funny thing which is happening here is in this range. You check, I am getting negative delta Ys, which is of course physically not possible. And the reason for that is again, second law of thermodynamics is getting violated over there. You see here, you expect the specific entropy of the refrigerant to increase during a throttling process. But here what I am seeing is the entropy is decreasing. Okay, so this portion of the calculation clearly shows that this part is not possible. So with that 2 millimeter diameter, I cannot have the requisite P evaporator equals to 12 and m dot equals to whatever was given. So I cannot have it. Even though mathematically, if you just sum it up, you may get some number, but you have to check the signs of the delta y. Negative delta y denotes that it is a physically impossible result. And the reason for that lies in the entropy. So the process is only possible till this point. So now what to do? You make another assumption for diameter and redo the problem. So your first assumption, that diameter assumption, you will have to change that and then revisit the same problem. Okay, so I have the code. If it works. A different version. Let's see what was the information given. Close this and make it open. So 0.02 kg per second is the m dot. And this is the condition which is given. Okay. So here I've divided into 50 parts, so you have more number of nodes here. So you see here negative values. Okay, and this negative value is due to this decreasing entropy. Okay, what was the assumption for the diameter? Let's see for my problem. So I started off with a diameter of 1.63. Okay, so let's go to a larger diameter. So problem is solved. So now you see here, okay. So here TL is not negative because your entropy is also continuously increasing. So you will have many such solutions. Okay, so if you change your diameter, you will get a different length. So there is no unique solution to this problem. But you have to ensure that you are not violating the second law of thermodynamics. You will not violate the first law because you have ensured, because you're solving the energy balance equation. So definitely you're not going to violate that. But there is a chance that you will violate the second law. And hence it is important to also get the output of entropy. Okay, so this is the crux of sizing a capillary tube. So you don't have to write a code in any exam or tutorial. So I'm just telling you how we actually size. Now Ashray has done a very important thing is they have tabulated the length and diameters for various refrigerants for various operating conditions. So in the field, if you have to size, you just have to look into that table or a chart. So they have given all the information in form of a table or a chart. But how that table or chart is created is through this process. Okay, so I hope at least you got a feel for how involved this calculation is. But finally, what you get is just the length and diameter. So any question? There is one obvious question which I will discuss now, but let's hear if you have any other questions. So any questions? Okay, no questions. So I was expecting then what is happening over here? Huh? At least you will ask that. Anyway, I'll tell you what is happening over here. Let's say I sum up all these lengths and I check what is the evaporator temperature here. It is 19.92. So if I were to use a 2 millimeter diameter of whatever this length is, I don't know whatever this sum is. Let's say it is 1.5 meter. Okay. So 2 millimeter diameter, 1.5 meter length, I will be sizing the capillary tube for this evaporator temperature and pressure. And let's say I place it in my system. Okay. Then see, the evaporator temperature can be lowered by lowering the by increasing the mass flow rate through the compressor, because as I told you, your system is the operating condition is decided by, of course, the load and how much your compressor is sucking in. So if your compressor is sucking in a lot of refrigerant, you can lower the evaporator pressure and hence the temperature. Then what is happening on the capillary side? What will be happening on the capillary side is, if I just denote it by one single length instead of that coil, just at the outlet of the capillary tube, you will have or just at the inner surface of the outlet of the capillary tube, you will have 570 kPa. But your evaporator pressure is low compared to this 570 kPa. Let's say it is 443 kPa. There will be a shock wave just at the exit of the capillary tube, and the pressure will suddenly decrease from 570 kPa to 443 kPa. Okay, so till the evaporator pressure of 570 kPa, your capillary tube at that particular condition is balanced with whatever your desired mass flow rate, that is 0.02 kg per second. But if you are demanding 0.02 kg per second at 443 kPa, okay, so this is what will happen. So this capillary can provide you 0.02 kPa, 0.02 kg per second at 570.7 kPa. Any further reduction in evaporator temperature will not change the mass flow rate. The capillary is right now choked, and at the exit you will have a shock wave which will then suddenly change the pressure from 570 kPa to 443 kPa. And you will hear some shrill sound. That's all you will hear. Okay, so if I were to plot the m dot at whatever 19.92 evaporator temperature, it will deliver 0.02 kg per second. After that, it is getting choked. So this condition is called the choked condition of the capillary tube. Okay. So if you want to avoid choking, then you will have to go with a different. So that is a larger diameter capillary tube. Okay, so you can see that going with the larger diameter ensured that your velocities are lower. Earlier, the velocities were more or less at this value at 19.9 kp. This velocity is called the critical velocity. It is a function of operating condition, it is a function of the fluid which is used. Okay, so by going with a larger diameter, you have reduced at 19 point whatever temperature, at temperature, you have lower velocities now. So flow is not getting choked. So this is the condition at the T equals to 12. If I ask you to size the same for, let's say, evaporator temperature of -20, you will see that this may also choke at -20. Okay, so this is one very common phenomena with any expansion device when it is operating well below the or well uh, below the designed evaporator temperature, or I should say that well above the desired pressure difference. So the pressure difference here is PC minus PE. So if this delta increases, there is a chance of choking. Okay, so you will see that if you increase this difference, the velocities increases. That's quite natural. If you apply a larger pressure drop across a tube, the velocities would be larger inside the tube. So if you increase this PC minus PA, uh, so I'm increasing this PC minus PE across the capillary tube, it increases, velocity increases, and at a particular velocity, critical velocity, it gets choked. Now further increase in PC minus PA, so it could be increase in PC or decrease in PE, whatever way you achieve it, is not going to change the velocities and hence the mass flow rate provided by your capillary. Okay, so then that capillary tube is called to be in the choked condition. So this is the characteristics of the mass flow rate provided by your capillary tube. And now remember that once this diameter is fixed, you cannot change. So that is the biggest issue with the capillary tube, which is fixed opening time. Let's say you had a valve and it got choked at a particular opening. You can increase the opening to bring it back to the non-choking flow condition. You do not have that provision over here. Yeah. So this is exactly what I had told you just now, that you can create such m dot versus TE curve for different TC. So if you maintain TC constant and continue to decrease your TE, which means that you are changing the PC minus P. So whenever we are discussing TC minus T, it is equivalent to PC minus P. So TC is constant, m dot TE. So if I reduce TE, I will be increasing the flow rate through the capillary, but only up to a certain length, only up to a certain TE. After that, it can choke. Okay, so there could be choking after this. Okay, the choking need not happen exactly at the same TE for all the condition. So this would be the characteristic of your capillary tube. So mass flow rate is totally dependent upon this pressure difference. So you have sized it for 45 and 12, and we were able to get this non-choking flow with this particular diameter. But suppose you operate this for -20 degrees C, there is a chance of this getting choked. Okay, so as I have told you, capillary devices cannot control its mass flow rate actively as the tube area is constant. So if this curve is fixed, that is what it will deliver. there is no provision for changing the area in order to change these curves. So this is for one TC. You will have for another TC, another TC. So such curves will be drawn. And these curves are given by ASHRAE for particular diameter and length of the tube. Okay. Now, as I told you, ideally what you would want is your capillary and your compressor should be providing you the exact mass flow rate that is desired at your operating condition. Now, if you recollect, the mass flow rate delivered by the compressor as a function of T for any particular TC was given by this curve. Oh, these are all rough curves. Okay, you do not have to scale it. So it was somewhat like this. TC constant, TE and m dot by the compressor. So if you decrease your TE, what happened was RP, that is PC over PE, increased, and hence your volumetric efficiencies were poor, plus your densities at the inlet of the compressor became poor, hence the mass flow rate was very low if you reduce your TE. Okay, so just focus on this particular blue and blue curve. So let's say for the same TC, I have drawn the curve for compressor, I have drawn the curve for capillary tube. Wherever these two curves are intersecting, that is my graphical solution to the two simultaneous equations. So I have one characteristic equation for the capillary tube, I have another characteristic equation for the compressor, and I ask you what is the evaporator temperature at which both these mass flow rates will be equal. So either you solve it mathematically or this is graphical solution. So you will get this point as your balanced condition. So this would be the balanced condition or balanced T evaporator for a particular capillary tube and whatever compressor you have size. Now suppose you do not change the capillary tube, you bring in a bigger compressor. Okay. So a bigger compressor means at the same evaporator temperature, it will be able to deliver more mass flow rate like this. Then your next balanced condition would be this one. So with a bigger compressor, you will have a balance at a lower evaporator temperature, which is quite intuitive. Because it will be able to suck in more refrigerant from the evaporator than the previous one. So your evaporator pressures and hence the temperatures would tend to lower. But now you are seeing the graphical evidence for that. Okay, so you have to decide, let's say for domestic refrigerator, I expect my evaporator to operate at -20. Okay, so if this intersection is happening as at -10 degrees C, so you will have balanced condition only at -10 degrees C. So that would be your steady operating condition. Okay, so if you want your evaporator to operate at -20 for a particular condensing temperature, then you have to size your capillary tube and compressor for that. If you bring in a bigger compressor, you will have a shift in evaporator temperature, or vice versa. If you bring in a different capillary tube also, which will deliver larger mass flow rate, that will also shift the balance condition. So instead of using this capillary tube, if you were to increase the diameter, so it will be able to deliver more mass flow rate. So then you will again have a new evaporating temperature. Okay, so by sizing all the components, I mean that everything should match at your desired operating condition. Okay. So now let's say you have sized your compressor and your evaporator for this condition. Now definitely you do not have control over the condensing temperature. Let's say your room temperature, this is for a domestic refrigerator, and your room temperature is now higher. You do not have air conditioning, and you're probably keeping, let's say, your refrigerator close to a window or something, and the ambient temperature is high, and hence your condensing temperatures are high. Then what would happen? So what will happen is simply for your capillary tube, this is the next characteristic line for that particular condensing temperature. Your compressor will deliver this much. So this will be your next balanced condition. If the condensing temperatures were to rise even further, this will be your next balanced condition. So now you see if your condensing temperature rises, your evaporator temperature is also rising. Okay, so if you want, yes, someone has a doubt. Okay, so if you want to operate at your operating condition and you had decided, okay, I have designed the condenser for this much as ambient temperature. If the ambient temperature changes, everything again starts to shift. Okay. But how this balanced condition is achieved, that itself is a complicated phenomenon. Okay, so let's say you have initially this as the balanced condition. For a particular TC1, you have this capillary tube which is fixed. It doesn't change. You have a particular compressor which is delivering this much amount of mass flow rate wherever these two intersect. This is your initial balanced condition. Now let's say due to some reason your condensing temperature has changed. Okay. So now your condensing temperature has changed. So at this particular evaporator temperature, your capillary will now start providing more mass flow rate. Suddenly your evaporator temperatures will not shift from here to here. So that is an eventual process, but it will take some time. So let us see how it goes or how it moves from this point to this point. So at this particular evaporator temperature, your capillary will be able to provide this much mass flow rate, whereas your compressor will only deliver this. So now there is a mismatch. Capillary device is providing more mass flow rate. So if so, let me draw the circuit again. So the amount of refrigerant being sucked by the compressor is low, whereas the amount of refrigerant which is provided by the capillary tube is high. Why? Because the condensing temperature has risen, hence the condensing pressure has risen, and immediately your evaporator temperatures will not go down. Okay, so your evaporator temperature is still the same. So the pressure difference across your capillary tube has increased. Hence, it will start to deliver more and more mass flow rate. So it is delivering this much mass flow rate across. So this system is able to deliver this much mass flow rate across the capillary tube, whereas compressor is only sucking in this much. So your evaporator will start to get flooded. Okay, your evaporator will start to get flooded. So your tubes will start to get pressurized. Okay, because in is more than out. So your evaporator is getting flooded, the tubes will start to become pressurized. Hence the pressure will start to increase in the evaporator side. Okay, let's say the pressure and hence the temperature increases to this value. Okay, now at this condition, my capillary tube will be able to provide this much of mass flow rate, and my, okay, let's not confuse this. So let's say it moves through this condition. So my capillary tube is providing this much mass flow rate, my compressor is providing this much mass flow rate. So the amount of imbalance has now reduced, and this continuously this pressure will rise till you attain the new balanced condition. So this balanced condition is attained due to an imbalance in the intermediate conditions. Okay, and during this process, the evaporator is getting flooded. Okay, and this is a cause of concern because if because of this flooding of the evaporator, there is more amount of liquid refrigerant entering into the evaporator than what the poor compressor is able to suck in, then there is a chance of the entire volume of the tubes of your evaporator getting filled with liquid refrigerant and the liquid spilling into the compressor. See, ultimately, you have a tube over it. Okay, your capillary tube is connected. It is filling up this with liquid plus vapor, and the vapor is getting sucked from here to the compressor. If this rate of filling is faster than the rate of suction by the compressor, there is a chance that your L plus V can reach up to this and get sucked into the compressor. Okay, so this is an issue with the capillary tube. If you use, you have to ensure that the amount of refrigerant inside is so little that it will not fill up the entire evaporator tube. Because if this entire evaporator tube gets filled with liquid and it goes into your compressor, then your compressor is gone. This is a major drawback of capillary tube. Okay, I'll stop here. We'll continue our discussion in the next class.